Okay, so welcome to PDEs lecture 3. What we're going to do today is go on with quasi-linear equations and look at some of the properties that generically arise in first-order systems. So just a reminder, the last time we were looking at Burger's equation, and I'm sort of going to use this as the basis of the discussion. So what we had is we started with Burger's equation. We found a parametric solution to that, namely we wrote down the initial velocity on the Cauchy curve, where x, it was an initial value problem here. At time t equals to 0, we chose x as the coordinate, and we said the profile was just h of s, and it could be anything. And then we went on, and from what we derived last time, we wrote down the characteristic differential equations, and we said we have to solve them. Remember that z potentially depends on time, except in this case it's dz dt 0, so we know that z is a constant, and that constant is simply a constant with respect to t, and that constant is simply h of s that depends on where along the Cauchy curve you shot your characteristic away. So just to help your intuition, in this plot on the left, the characteristic curves are the magenta or the purple curves, and the actual solution is at a given time is given in blue. Okay, so what we did is we solved the characteristic equations. First solved the one for z, so we had z equals to h of s. Then we solved this one, dy dt equals to 1, so y is equals to t plus a constant. And we know t equals to 0. From there, the constant is 0, so y is simply equals to t. And finally, we left with dx dt is equals to z, which we now know is a constant or a function of s only. We integrate it, so we get that it is zt plus a constant, and that constant is s, depending on where we are on the Cauchy curve. So we have that x equals to s plus zt. We then went on and we eliminated s and t, and we got this implicit equation where u equals to h of x minus uy, and so we implicitly have u as a function of x and y, except that it's a bit tricky because we know what h is, but u is in here, so if h is complicated, it's not such an easy function to evaluate. But nonetheless, I said we could draw the curves. And the way I drew the curves was exactly like this. I basically drew the characteristics first, and before I even drew the characteristics, I drew what was the characteristic projection, namely the projection of one of these curves into the xy plane. Okay, so simply shine a light from above. Shine a light from above, then the characteristic projection is simply what the curve looks like if you've put it on the xy plane. And I said that is easy to derive, and the way I did it is I looked only at the y and the x functions, and I eliminated t from it firstly. So I said t is equals to y, so x is equals to s plus z, which is simply h of s times y. So I got this. And so for each s, in other words, each point along this curve, the characteristic projection to the xy plane is just a straight line, and the line's slope depends on h of s. Okay, so the line's slope depends on the initial condition. And then I said along these lines, and z also depends on which line you're on, along these lines u remains constant, and that's how we actually drew this picture. So I basically got the initial curve, and you can do a different thing for a different initial curve, and you can in fact practice it and do it yourself. I got the initial curve, I worked out what these characteristic lines were, and then just propagated the height. Look at along these lines, the height remains the same. So I have basically a wire frame that is making up my solution. Right, and so what we're going to do today is look at some of the generic properties that can appear in the most general nonlinear first order PDE with one dependent variable. Okay, and the first thing you can note is that what happens with this curve is the wave that has the highest initial condition tends to travel faster. Okay, so if, for example, here the initial shape was symmetrical. Suppose you started this thing. The thing at the top of the curve is going to actually travel faster because the slope of this characteristic projection into the xy plane, in other words, this line down there, is bigger than the one behind it. Okay, so these guys travel faster, and what happens then is that this initial slope, the higher ones tend to catch up with the other ones, and eventually they tend to break over. So this thing was a very simple model for how a wave breaks. Okay, and you can actually see it happening. In fact, it's one of the first places where it was understood, where you literally have the velocity at the top of the wave faster than the velocity at the below, which is usually true when you're working in shallow water, where the friction with the ocean floor retards the lower velocity, and then the top ones keep going, and eventually they crash over. And so something very weird happens when the wave over here gets vertical, and we're going to work out the exact conditions in a moment. When the wave gets vertical, then you have no longer got a one-to-one surface, right? It gets multivalued, right? So if you look here, where this wave actually goes, it's going to make like an S shape as it goes on.
Can you go back to what do you mean by
A multivalued surface, okay? A surface that's just a smooth hump is single valued. For each point on the surface, you can project it down, and you are identified with a unique point. But if you have a surface that's like a folded paper, okay, so it does that, then you're going to pierce the surface through 3 points, and that's what I mean by multivalued in this case. Okay, so when that happened, it's no longer a well-defined surface, and then we need tricks to actually deal with it. Okay, sometimes if you're dealing with light, it still has meaning, but most of the time what happens then is we form what we call a shock wave, where the solution actually jumps. And we see this in fluid dynamics a lot. In fact, if you'll see from the next slide, I'm going to argue that it's actually generic for any type of PDE. You get these shocks that occur. And so what today's lecture is going to be about is simply to give you an idea of how we actually analyze the thing to get a handle on the shocks, what some of their properties are, and also the fact that we can still find a solution even though this thing is behaving strangely. And the way we do it is we patch two well-behaved solutions together, except on a single line. Okay, and I'll show you how that happens now. But this is just to remind you of what we did last time and to get the engine going again. Okay, so just remember last time, this is our initial value curve. You've already seen it. It's just a hump function. You could have chosen any function. And then here are our characteristic projection lines. Okay, and I said you run into trouble because look what happens. Here, remember, along the line, the curve's value or the solution's value propagates along. So over here, it's easy, right? You have the solution, it propagates out there, it propagates out there. So you know exactly what the solution is. There's no ambiguity. The same over here, right? This solution comes from this initial condition. The problem over here, there, is that you have several lines that are lying on top of each other, and this is where your single valuedness of the solution fails, and in some physical cases the solution actually breaks down, and then you've got to choose what solution you're going to have. Okay, so the first thing we want to do is find out where we actually have the problem, right? And the way we calculate where we have the problem is simply we have the two lines. We can say, let's take any two curves That's our characteristic projection. We know both of the lines obey this equation, depending on where you have started. Okay, and we want to now find out where they intersect. Okay, so that will give us the solution. And this is any two lines. I could have started with this one and that one, in which case they'll intersect very far out. But if I started with this one and this one, they wouldn't intersect. So I want to be able to know. I'm more interested in where they do intersect, so actually let's get it. Okay, and you can do that simply by writing down this equation for CS1, where S1 is the constant, and the second equation for CS2, where you now start at S2, and you equate them, and you eliminate x. Okay, and then you'll get x is equals to a value, and you'll get y is equals to this value where you eliminate it. It's simply finding the intersection point of the curves. So let's now look at this expression. And if S1 and S2, remember they are your parameter along the Cauchy curve, namely where in the initial condition you are. If you let them go get infinitely close, what does this expression remind you of? Okay, this is an expression for y where the two lines intersect. Okay, and this is true for any S1 and S2. If the two get infinitely close, S1 and S2, what does this expression mean? Think about it. I'll get back to it. Okay. Before I go on is another statement. If H has compact support, do you know what compact support is? Okay. Compact support is what happens if your function is stuck to a small region. Okay. In other words, a bump function like that has compact support. There's a region, you can give a more rigorous definition than that, basically that it falls off to infinity with a certain speed ultimately. But the basic idea is the function is contained in a certain region where it's strongly non-zero and then basically falls off to zero at infinity.
So like a normal function.
A normal distribution, a function that does this and then goes to zero. Most physical things we view of as having compact support because they are localized to a region. Okay, and the rigorous definition is basically that the function and say its derivative goes to zero, but they're more way. But that's all you need for now. So the statement is, if the function is localized, then this thing u, the solution, becomes singular whenever these lines intersect. Okay, and what it also says, if this function is localized, it's basically always going to happen. Okay, do you see why? So the first observation is this thing, remember the definition of a derivative. Okay, so this is just 1 over the derivative if S1 approaches S2. Okay, so now the statement is if H has compact support, there is always going to be a region where the derivative is negative. Okay, so look at this. Here the derivative is positive, is increasing. The characteristics that come in this equation tend to flare away from each other, so they're not going to intersect. But where the derivative is negative, okay, there's a possibility that they intersect. It doesn't always happen, like far out it's not going to happen, but over here the thing is going to intersect, and the reason why you need the derivative to be negative is that y we've assumed is bigger than 0 because it's an initial value problem. You start at y equals to 0 and then y steps forward. So for us to get an intersection that's y is bigger, this thing tends to approach the derivative if the lines gets close. And so this guy, if it's negative, you at least have the chance of an intersection. Okay? And any function that is localized to a spot is always going to have increase and then it's always going to decrease to 0. Therefore, it's always going to have a negative derivative at some point, and therefore its characteristics are most likely going to collide, And therefore you can state this feature, inconvenient as it may be that the problem is no longer single valued, is in some sense generic. Okay, you get shocks. Shocks is not a strange thing. It forms in almost every PDE, and we need to have some way of dealing with it. Okay, so the high velocity points collide with the lower velocity points in front if you just want a physical feeling for it. And what you then have is this picture I showed you on the previous slide, where these guys start breaking over and these guys are slowed down. And just another way of looking at it as well is, let's have a look at what, so PDEs is something, you get an answer, you get different ways of looking at it, and you try to extract the truth in painful, like little strands of spaghetti. You pull them out and you savor them. Let's now have a look at this function u equals to h of x minus uy. So this is our implicit definition of u from the Burger's equation. And we can see we run into trouble here in the characteristic picture, just the characteristic projections. We see there's problems simply when the characteristics collide. But we can also see from this thing, the place where the problems start is where this thing goes vertical and the derivative becomes infinite. So let's try and work out that point as well. And what we can do is compute the full derivative with respect to x over here. Okay, so the way we do that is du dx is equals to d dx of this side, and now we use the chain rule. It is simply the derivative of h with respect to this argument, so the h ds, and then it is times basically the interior one, so that's 1 minus du dxy. Okay, so we get an expression for du dx, and ux is over here, and ux is over there, and we simply solve for du dx, and we get that it's equals to this expression. Okay, and so what we have now is that this thing becomes infinite. In other words, these lines become vertical if this guy, the denominator, is 0. If y equals to 1 minus 1 over h prime of s. And lo and behold, it's exactly the same answer that we derived here, just in the limiting case. Okay, so the two pictures are consistent. Here we're simply looking at the characteristics where they collide and working out the intersection point. And here we used a different argument looking at the full 3D thing, but the picture is consistent. Whenever y equals to minus 1 over h prime of s for this particular problem, we're going to have basically our characteristics colliding, the surface is going to have vertical, and we're going to have what we call a shock. A literal, like a, hopefully not just at the complexity of the problem. So what we can do now is we can also go about and we can work out the smallest value of y for which the shock occurs. Okay? And the smallest value for y for which the shock occurs is simply what I call y star. Okay? And the smallest value for y where it occurs is going to be the biggest derivative h bar of s that you can obtain for this problem. And we're going to say that occurs at s0. So you can have a look at this thing and you can work out where this thing derivative is largest, and that will give you the smallest value of y. Okay? Sorry. Well, largest in magnitude. Okay, so h of s is a minimum, is where y star occurs. Okay, so this thing we call not just a shock, as I mentioned earlier on, but we call it gradient catastrophe. And the reason we call it gradient catastrophe is basically that this thing has a catastrophic jump from one to the other. Okay, so know how to work these things out, know where they form. Go through this problem yourself, and you'll have the opportunity in your problem sets to do one as well. So what we now want to do, we've shown that shock waves are generic. I've argued it below over there that they occur in almost any single problem. We've given it names. Let's see what we do about them. Okay, so here I've just cleared up the picture a bit. This is the wave front at different times. So it just shows it more clearly in that 3D picture. There's our initial condition. Here we have the case where the top velocity, the points at the top have a bigger velocity than the points at the bottom, so the top of the wave tends to catch up with a foot. And over here you've gone, this is where the gradient catastrophe occurs, and so you can work out that value, and then here it actually bends over and you've got to figure out how to deal with that. Okay, so here's another rigorous statement. When the characteristics collide, and that is the characteristic projection in the xy plane, there's no strict solution of class C1. In other words, your piercing thing fails and you have this folding over and you've got to figure out what to do with it. So the solution is multi-valued for a given x and y and shocks form. Okay, so I'm just writing down what I've said already. And this is, as I said, is typical behavior for nonlinear PDEs, and we want to be able to deal with it. So what now is possible is we can define a weak solution. And it's not only possible mathematically, we see it happening in real life physics. And I'll show you a number of pictures of it. It's kind of amazing where these things occur. So it's possible to find a weak solution. And so that's what we're going to do now, and just get you a feeling for it. So this is no longer C1, so it hasn't got a continuous derivatives everywhere. And the way we do it is we basically say, and this is, we suppose the characteristics collide along a line like this. Okay? Then we say everywhere on this side, the solution is propagated from this initial value, and it's fine. And everywhere from that side, the solution comes from these initial conditions, and that's fine. And we have this boundary in between that we call the shock front. Okay, and then we make the weak solution that way. So it's basically a solution that is stitched together along from things that have traveled along characteristics. So another way of viewing your characteristics are the curves along which your solution propagates, right? You start with your Cauchy curve at the bottom, and the information travels along these characteristics. So you basically populate the one section with characteristics attached to the initial curve over here, and the second section with characteristics attached to this initial curve over there. Okay, what do you think the initial condition is that causes this solution?
I'm not sure how to explain it. But I would assume there's something to the characteristic, characteristic equations, curves. They intersect at some point. I'm not just sure how to explain.
Okay, so remember I said the characteristic curves for Berger's equation is dependent on the initial value, right? Because the slope of the curves, you had that x is equals to hsy plus s. Okay, so that's what's happening over here. So what I've done is I chose an initial velocity profile like this that's not a hump. Okay, in other words, it simply has an initial velocity like that fixed at 1, an initial velocity like this fixed at the bottom, and this is the initial profile.
Is the jump that you spoke of when you said it just jumps sort of
With a KdV equation? Yes, eventually this goes in that, but just leave that for now. Yes, it's a good example, but we'll discuss that right at the end. But yeah, it's the type of profile you get if you had a tank of water and you would just like lift the thing out. Okay. And part of this thing has very much got to do with that discussion eventually. But let's just keep it. Let's just stick to the problem in front of us. So this profile or these characteristics you get if you're solving Berger's equation and you choose this initial velocity profile. Just one careful thing, this thing hasn't got compact support, right? Okay, it's just for me to get the definitions from the previous one. It's an example. It doesn't have compact support. The only reason I'm doing it is to illustrate how to deal with shocks. Okay, so that statement that shocks are generic comes from the assumption, or you can only prove, it happens in other cases, but you need compact support, and this is an example of a function that does not have it. Okay, so here you have it. Everything on this side, the slope h of s is bigger, right? And on this side, the slope h of s is less, is basically a half, and therefore you have these characteristic curves. So now what we want to do is we want to actually analyze what happens at the junction. Okay, and that we call the shock speed, basically how this junction moves as the characteristics change. And to analyze the shock speed, what we're going to do is, remember I said we were dealing with Berger's equation, but it had another way of writing it. And so we're going to use the second way of writing it to actually derive what the shock speed is. And so I said, let's simply, so this is what this profile is like. Let's simply say we start with an initial condition h of s, which is equals to the velocity u left. So here, in this case, u left is 1.5. If s is less than 0, and u right, which in this case is 0.5, u r if s is greater than 0. Okay, so this is just an example of how we try and capture the shock, and then I'm going to derive the more general formulation afterwards. Okay, and so this is what we call a step function, just a rescaled one. And we have that the u left is greater than u right. In other words, this guy behind is bigger than this guy in front. And that's important because we see clearly that we only have shocks if the top one, this one is bigger. You can go and work out for yourself what would happen if you reversed it. That's also actually an interesting problem. But it doesn't result in shocks. Okay, so what we then have is we are going to go and write down the answer. So the reason why this example is useful is that these guys are basically, we're going to go to the implicit equation, and these guys are constants. So what we're going to have is the solution is going to be u as a function of x and y, h of x minus cy, okay, because u is either u left or u right, and that gets propagated along the characteristics. And cy, we know when we're on this side, is simply going to be u left. And if we're on that side, is simply going to be u right. But what's going to happen in here? Okay, so we said it's a step function. We know we basically have one solution on the left, one solution on the right. In between, here's a transition that's moving with a certain speed. Okay, so, and this speed, c, we're going to say is the speed of the shock front. It's not going to be u left or u right. It's going to be, well, we're going to derive what it's going to be. Okay. So what we now want to do is, the technique we use here and the technique we use later on is saying, let's choose a constant m that's very large, and we integrate this equation. Okay, so the reason we do that is, remember, we definitely can't differentiate the equation because it's not continuous, it's not C1. So what we're going to do is we're going to seek what we call a weak solution, a solution that satisfies the equations on average in an integral way rather than exactly at every point. Okay, so we're going to choose m as a constant and we're going to integrate this equation. Okay, and so there we have it. And we just rigorously write it down. So the integral from minus m to m, so we start very far out over here and very far out over there, of u dy dx, okay, is equals to minus a half, the integral from minus m to m, u squared, its derivative with respect to x, times dx. Okay, and this is convenient because we have a derivative there and we are integrating over the thing, so that is nice. Okay, and this other side we're going to massage a little bit, right? Because we assume the function is continuous, even though it's not differentiable, we can take d dy out, and then we have the integral from minus m to m of u dx. Okay, so in some sense, the averaged value of u between minus m and m, and we can see that that is going to be equal to this thing that's a complete differential just evaluated at the boundary. And so if we evaluate u squared at m, right, m is positive, so we basically have that if it's evaluated at m, it's over here, so you have u right, but it is minus, so there we have minus a half u right squared. If we evaluate it at minus m, so we're evaluating it over here, it's u left squared, okay, minus, and then minus over there, sorry, minus because it's the negative part of the integral, so it's plus ul squared. Okay, so the averaged value changing in y is simply the difference between the two speeds on the left and the right. And that we can kind of expect because the one is faster and it's catching up on the one that's slow, so the difference is to be expected. So now let's have a look at simply this part over here. So this guy, m, the integral between minus m and m of u dx, you can simply write as follows, right? At every time y. Why do we write it that way? Okay, so let's not start at the initial condition. So first, okay, let's first do it at the initial. At the initial condition, right, this shock over here is at 0 and y is equals to 0. So at the initial condition, this integral is simply m times u left, in other words, everything underneath here, plus m times u right, m times u left, everything underneath here, plus m times u right, everything underneath there. So it's the right answer.
Can we start again?
Okay.
Just
The grey bit. Okay, so this integral that we want to do, we basically want to integrate from minus m to m over dx of u. Okay, so we want to take the integral, if y is 0, we want to take the integral over here. So it's everything underneath the graph. In other words, it's everything underneath over here. Okay, so that is simply m times u left plus m times u right. Okay, so you're happy with me if y is equals to 0? Okay. If y is not equals to 0, what we've got to do is, remember, the solution propagates along these curves. So we've got to integrate along here all the way till we get to the shock. Okay. And so there it's going to be u left, and we integrate to there, times m, plus however far the shock has moved in that time. Okay, and that's where the cy comes from. So this additional part is the shock is no longer at 0, it's moved to this position, and the distance it has moved is simply cy. Okay, because the shock is this red line, which is basically x minus cy.
I'm trying to think of it as like using the top graph as a particle just sort of moving as well.
Yeah, this here over here, what's literally happened is this front has moved to that new position, and the distance it has moved is simply c times the time that's elapsed. Okay, so that's where this thing comes from. Then the second part, the u right part, is you want everything on the right over here, which is simply m times ur, but you're not going back to the origin, you are stopping over here at the shock front. So it's less than it was initially, so you have minus cy, namely the distance the shock front has moved. Okay, and so what you get now is you basically now have an equation, because you've evaluated this thing. You can take the derivative with respect to y. Okay, and if you take the derivative with respect to y, this m that you chose that was constant, it disappears. And so what you're left with is that c times UL minus UR is equals to this thing. Okay, and then you can simply divide by UL minus UR over there.
So the dy, you took it to
Yeah, I take ddy of this thing, and then I know that it's equals to that guy. Okay, and then I get what my C is. And you can see, if I want the solution to satisfy the equation on average, not precisely at every point, but on average, then this shock will be moving at a speed that is dependent on basically u left plus u right over 2. It will be moving at the average of the two initial velocities. This derivation is true for Berger's equation with this initial condition. However, this property generalizes. I just wanted to give you a simple example to show you how it arises, but before we get hidden in the mathematics of how you do it in general. But it generalizes to shocks fronts, all shocks fronts. And there's some pretty remarkable sort of descriptions you can get of shock fronts. I'm going to do the most basic one, but know that it's actually a field of study that you can go on. Shocks are very, very difficult to capture numerically. If you integrate the equations, the fluid equations or so, numerically, shocks are a problem. And so having solutions we can solve it exactly, people calibrate their codes on, but they remain a problem. They're difficult to capture numerically. Because, and the reason it's hard, is because these things become really steep. Okay, so that's why the numerical problems arise, but there are a lot of analytic tools to actually deal with them analytically, and these have then been put into numerical codes to try and cope with it better there. Okay, so shock happens a lot when we simulate stars. It happens a lot when we simulate planes that go faster than the speed of sound. Because the speed of sound, and I'll show you beautiful pictures, are a shock wave. It's literally the characteristics in your fluid equation that are colliding when you break the sound barrier. And so the simple example gives you a way of ultimately thinking about that if you want to start studying that more seriously. Okay, questions here about this example before I make it more general and more complicated?
I think the explanation on how it works with sound is
okay, good. Let's go on. So now I'm going to do a slightly more general problem. I'm going to look at these weak solutions that basically extend the solution beyond the gradient catastrophe, and it's going to be exactly that analogy that I've just given you, just generalized. Okay, and what I'm going to do is I'm going to look at a slightly bigger class of equations than Berger's equations. In fact, I'm going to look at all equations that have this particular property. So firstly, before I introduce the property, is suppose I'm going to call divergence form basically the following property. Suppose I have one function of u, and u is obviously a function of x and y. So I call it r, and I have the property that dr of u dy plus some other function of u, its derivative with respect to x. So ds du dy, the partial derivative of s of u with respect to x. Sorry, that's x, not y. If that is equals to 0, and s and r obey the following thing. In other words, s's complete derivative with respect to u is equals to u times r's complete derivative with respect to u. Okay, so that's what I'm assuming, and this is going to be true for all the solutions that I solve in this way. Similar things exist for other problems, but we're going to just restrict our discussion to something that's easily illustrated for a while. Okay, then I'm going to be able, then I'll construct a weak solution for you, very similar to what I've just done in the example. Okay, so the first comment is things that look like equation 1, if you get them in physics, is typically an example of a conservation law. And basically, for a conservation law, what I mean is for any a, b, and y, the following is true. Okay, so for any a, b, and y, a and b are now the boundaries, okay? They are constants. Y is a particular time slice, just like we did with the initial condition and then later on. We can do the same thing, and it's just a generalized version of that. So for any a, b, and y, we have the integral of the ddy of the integral from a to b of r is equals to minus s evaluated at, is equals to s of u evaluated at the boundaries a and b. Okay, do you see how that arises? Okay, let's have a look at it. Look at this equation and integrate it from a to b. Okay, then you can do exactly the same trick that we did in the previous slide. If you integrate this thing from a to b, you can, and you assume that r of u is finite, you can take ddy outside. So you're left with ddy, the integral from a to b of r. Okay, so you're happy with this side now. And you can say that is equals to minus the integral of a to b ddx of s and u. And because it's a derivative, you can just differential with respect to x, and you're integrating it with respect to x. You can simply evaluate s, so you can simply evaluate u on the boundaries, namely s of u of a of y minus, because the thing is below, but you have a minus sign in front, so it becomes plus. Okay, and then here is the thing evaluated at the second boundary. Okay, so it's just a generalization of what we got for the previous in the previous case. Okay, and that's what I call a conservation law that you can get, where you can have an integral expression of your equation equals to this difference. Okay, and so what we're now going to do is we're going to derive what we call the Rankine-Yugiro shock condition. It's a condition that we saw illustrated in the previous slide that connects the shock's boundary or the shock speed to what's happening on either side of the boundary. Okay, and it's more general just to that than that just special case, and you can see how we get it now. Okay, so once again we're going to say let us suppose that u is a continuous one solution of 1. Okay, in other words, it's a solution that we can get from the characteristics amongst other things. And it's clearly not, we're going to look at shock, so it's clearly not continuous solution of 1 over the whole place. But in other words, it's made out of 2 bits. It's continuous solution C1 in 2 regions, the one on the left side and the one on the right side of the XY plane. But on the boundary between it need not necessarily be. In fact, we've shown it usually arises that it can't be. Okay, so we have this idea that we can construct U from the characteristics on the left-hand side and the characteristics on the right-hand side in 2 regions, but we want to know how the 2 join together. Okay, and let us say these 2 solutions are separated out by this curve x of cy. Okay, so that's any generic curve. It need not be a straight line. In the previous example, it was that red straight line that we had. But we're just going to write it this way. So what we're going to do now is we're going to want to join these 2 solutions. So we know across this curve where the shock occurs, the solution jumps. Okay? And we're going to denote the limits of u from the left and from the right as u left and u right. Okay, so we are no longer doing with a special case where u is constant everywhere. We're only doing with a case where we know there's a jump, and the u that was propagated from the characteristics on the left, we're going to call that value of the jump u left, and the u that was propagated from the characteristics on the right, we're going to call that value u right. And remember, it can always happen because you always propagate the solution along the characteristics. So you can always find the value, but that value might change with y. Okay, but for a given for a given y, you're always going to have a u left and you're always going to have a u right, and that's going to depend on the initial condition that is connected to that point via the characteristic. Okay, and so what we're now going to do is very much the same as the previous example. We're going to choose A to be less than, and generally much less than, c of y, and B to be bigger. Okay, so in the previous example, both A was minus m and B was m. Okay, so now we're once again to use this conservation law, and we're going to say d dy, the integral from A to B of r dx, is simply equals to, we're going to write it out, okay, and we're going to write it out exactly the same as we did in the previous case, just being careful because now the function is not a constant. So it's going to be the integral from A to c, because we know what that is, and it's smoothly propagated from our initial conditions there, plus the integral from c to b. Okay. And we want to take d dy of this thing. So, and then we're going to have that is, we simply take the derivative now. So this thing is equals to c prime, okay, times u left, minus the integral from A to c, ddx of s, sorry, ds dx dx, okay, minus c prime r, u of r, okay, minus this thing. Where does that come from? Okay, so here is where it gets tricky. Remember, c is on the boundary, but c depends on y. So if you take the derivative of something where the boundary depends on y, you first take the derivative of the boundary and evaluate the thing on the boundary. Okay, and then you use the chain rule, and then you add the second component where you look at how the thing changes inside. Okay, so if you have not encountered this before, go and check it, but it is true. So we're taking d dy of this beast, okay? Maybe the easiest example is, suppose you have an integral from 0 to y of a function of x dx, right? And you take the derivative of that with respect to y, right? Then that is simply the function evaluated at the boundary. Okay, so that's what's happening over here, except that now the function is, c is a function of y. So that's where the first term comes from, okay? And the second part is, this thing can depend on y, but r can also depend on y. So then we keep the integral, and we say, we take d dy inside, and we see how it changes, how r changes. But we know dr dy is equals to ds dx from inside here. And so this is where the second term comes from. Right. That one you see, this one,
it was just a bit tricky, but I also
you see it now.
It's often integrated in terms of x, and then you can't differentiate in terms of y.
At the top. Yeah, so make sure, if you still have doubts, make sure you know what varying the boundary is if you differentiate it. But that's where this first term comes from. Okay, so now we have this full expression. Let us go about and evaluate it. Okay, and so what we now have is this thing for the right-hand side that we've written out. We have this thing on the left-hand side, and let's simplify expression 2. So what we then get is basically that C of R is equals to prime equals to R of u left minus R of u right. That comes from this. Okay. Minus this thing evaluated at A and at C. Okay. But that's going to fall away. The one evaluated at A is going to fall away with this one. So we're only interested at the thing evaluated at C, and that is simply S. If you're coming from the left, it's simply S of u left. Okay, so that's where that term comes from. This A boundary cancelled out with that one. Okay, and then over here we have that the integral from C to B, we want to evaluate it. And since we have the S dx, we can simply evaluate S at the boundaries. So we have S at xc on the right, minus because it's a lower branch, so it's plus there. And we have S evaluated at B on the right. Okay, so there, but that is going to cancel out with this guy, and so we're left with this expression. And so we have that xc prime, in other words, how the shock changes in time, its position, which is effectively its speed, is given by this expression, which is only dependent on the value of the solution on the left and the right of the problem. Okay, so the boundary terms of S at A and B cancel. The shock condition, which connects the propagation speed of propagation of the shock, which is simply dx dy, is simply the speed of which the discontinuity, and it's related to the size of the jump across the shock by the following expression. Okay, the other results that I'm not going to derive is you can prove using the characteristics, but you can just think of it generically, that these shocks are always infinitely small, okay, and they always confine into the small region, they always propagate, and outside is entirely fine. So you basically, when you have shocks, you don't panic, you simply stitch the solution coming from the characteristics that are connected to the Cauchy curve on the left to the solution with a that comes from the characteristic curves connected to the Cauchy curve on the right, and you work out what the value is, and then you know that the shock speed is going to be determined by how this actual solution jumps on the left and on the right. Okay, pretty. Huh? It's compact, but it's pretty, and it occurs everywhere. So I'm going to basically end with giving you some examples of shocks. The PDEs are slightly more complicated, but the beauty of the shock wave is that it's local. In other words, the way it's propagating forward, its speed, is dependent only on the two solutions. So, for example, this is an example of the mushroom cloud from one of the nuclear tests. We saw a cloud like that. Do you remember there was an explosion in Beirut not too long ago?
We felt it on the other side. I think, yeah, I remember.
Yeah. If you look, the one that was on the harbour that they
said it was firecrackers, it wasn't a terrorist attack.
I'm not sure if it's firecrackers. What happened was previously there was a ship that had a whole bunch of fertilizer that went there, and because you can. So the amazing thing is, and this is something I've done. This is also kind of a cool project. You can, because the shock wave is dependent only on the solutions on both boundaries, and because most shocks that explode in air become spherical, you can actually work out the speed of the shock, and that speed of the shock is ultimately dependent on your initial conditions. And if you have a spherical shock like that, it started at a point, so you can actually work out the total amount of energy from the speed of the shock that actually needs to blow it apart. So you can actually look at the videos of the Beirut explosion, and you can see there are various shock waves, but there's one time where it's like a cloud, that round cloud, that round cloud, what happens there is the shock wave is propagating through the air and is literally smashing the particles into the shock front. And you have this beautiful round cloud. And that front, the roundness is caused by the shock wave, because eventually, also from just that condition, you can prove that if in 3 dimensions, the shock front always wants to become spherical initially if the explosion is strong enough. And so you can look at that shock front, measure how fast it's going, and try and infer what the initial blast is. So a lot of people knew what the cargo load of the ship was. And you can then try and calculate how much of that actually exploded into the explosion and how much of that was actually not there completely by just looking at the videos. It's a little bit more complicated than that, because if you have a shock wave like that, some of the shock is going to go into the atmosphere and cause the round bubble, and the rest of the shock is going to propagate through the earth. Okay, and so you've got to know what percentage of energy went up into the bubble and which one went through the earth. And there's actually a way you can calculate that too, but I haven't done it. I wanted a student to try and do it. There was a car that jumped literally like 2 or 3 stories. You actually have this video, and you can see the shock coming through the building, through the ground as the buildings crumple. So you can work out that shock speed as well, and try and guess and try and estimate what part of the shockwave went through the soil. Anyway, the shockwave comes along and it literally bounced this car like a story up. So it was a tremendously powerful explosion.
So that was also the tank down in Joburg.
Yeah.
So we could also calculate how the shockwave happened, how just by the load and how fast it is moving.
If it's gone spherical. I mean, so it's easy to calculate if it's gone spherical. If it's not, then it's more complicated. Then you have to find actually the solution. So the beauty of this spherical shockwave, so I want to say, in principle, yes. In practice, there's certain circumstances where it's easy to calculate.
But I could use this method to approximate.
Yes, you could. As a first approximation, you could definitely do that. I mean, the shockwave method, we use a lot when we do astronomy. We have stars exploding, and then you can see how every year the thing gets bigger. And then so you know the shock speed, and once again you can work out what the explosion is like. There's this famous discussion of when they conducted the first test. You had Enrico Fermi, like he was one of the last great physicists that was really good at doing practical stuff and doing theoretical calculations. And they wanted to, the first test that they conducted at Los Alamos, they wanted to know how much power the explosion put out. So they had, I don't know, the little boy or fat man or whatever. They had the explosion, and then they had a whole bunch of sensors they put up around, and they wanted to actually estimate the power. And because they didn't have strong computers at that time, just 1 or 2, it would take a long time. So Fermi was sitting there with a stopwatch, and he was dropping little pieces of paper with a certain rate. And then afterwards, he simply, as the shock front came past, and afterwards he simply went and saw how far the papers had gone. And based on that single little papers, he then went about and he said, this is the energy output. Within like 5 minutes of the explosion, this is the energy output that the explosion did. And he was basically using this concept of the shock jump condition. And I think it's like 2 or 3 months later, the actual people that did the real hard calculation came out with a number, and they was in 10% of what Fermi had done. Okay, so yeah, you can get a very good estimate often by just making this approximation. Okay, and if that's something you're interested in, it's a good essay as well. Okay, so that's an example of a shock wave, a spherical one, where you've had a central explosion. Another example is that I like astronomy and I like explosions and stuff. This is a non-spherical shock, right? This is harder to model than that one and harder to calculate with, but still, as a 0th order approximation, you can choose things. So something happened to push these lobes out in like a dumbbell direction. I think this is Eta Carina, I'm not sure. It's one of the most beautiful nebulae that there are. And so what typically happens with stars when they start burning a new type of fuel, right? So stars burn hydrogen to helium. Then when they've run out of fuel, they tend to collapse. And they keep going like this all the way till they get to iron. But once they go past iron, there's no more longer energy output, so then they collapse catastrophically. And so what happens is the outside amount of gas doesn't realize that the inner star is collapsing. So it can no longer burn stuff. So the inner core begins to collapse and shrink like that. And the outer things are like, what's going on? And then suddenly like, oh, we've got nothing more to stand on. And then they collapse catastrophically in the middle. And then what eventually happens is they hit the central thing, they knock it, they call it core bounce, and then they shoot out. And that change causes a shockwave. And that shockwave then, as they go out, they not only, then they hit all the gas that's still coming in. So they basically have the solution that's pushing out, and whenever gas hits something, it gives off light. And that's what's causing this, those pictures, where you actually have the shockwave propagating out against the gas that's falling in. Okay, another example, a Concorde or a Boeing that's gone through the sound barrier. Right, and here is an example of a shock. It's a bow shock that basically you can actually see. So what happens when we look at fluids, the characteristics are once again the lines along which information propagate. So when you go through like a shock like that in the fluids, you literally have your characteristics bunching up against, getting very, very close. The faster you go, you sort of squash the characteristics together. And then you get to the point where you actually pierce them. And when you do that, you have a sonic boom. Like whenever you break the sound barrier, it's like goes bang. It's a shock wave that goes out. And there you can actually see it. And then it propagates outwards like that from the point that's actually pierced it. And when the Concorde started flying, there's a rule that you're not allowed to break the sound barrier above a big city. There's a certain radius around all cities where you're not allowed to go supersonic, or in fact come back, because you also make a little bit of a shock then. Because if you were to do that, you would simply shatter all the windows in the city. But here is a very nice picture of you actually seeing the density fluctuations and the shock wave that's coming off the tip of that thing. The other thing is when you actually punch through, if you've seen like these stealth fighter jets, they have this very, very fine point. Okay? And the whole nose is designed so that you have minimal shock wave running around your aircraft, because the shock wave is immensely powerful. When the solution jumps like that, all your gradients basically approach infinity, and they tend to rip things apart. So you have this very fine, that the shock starts along this point, and that like literally makes like this hole that gets bigger. And all it is, from a mathematical perspective, is the nature of your characteristics are colliding, and you are, as you'll hear later on, actually changing the type of the differential equation you're solving. So, and the final story, now that I've given you pictures of what shock waves looks like, and we've done the most simple calculation, which I'm hoping you're going to redo on your own, just to make it your own. This is a story also that comes from the nuclear bomb, is how you control a shock wave. Okay, so I said it's a speed on the left and the right of the front of the shock. Okay, and so the problem existed when they were building nuclear bombs. So the plan is you have your uranium core inside, say it's all this gray stuff, okay, and you want to compress the core so that you start your thermonuclear reaction and so that it then explodes. Okay, and so the way they did it is fine. The way you can compress something is you can simply make an explosion around it, it squashes everything together, and then you're done. Except that didn't work, right? And the reason it didn't work is, look what happens. Suppose you can't have a uniform explosion, so you're going to have little places where you have detonators, okay? And you can't even have infinitely many of them. So there's going to be a place where you detonate it, and then when you detonate it, the shock's going to look like this. It's simply going to be a round thing that starts traveling. And so what happens, suppose you have one spot over here and one spot over there. You're going to detonate it, and you're going to basically have these two round curves going in to hit the thing over here. And then what's going to happen, or what did happen, is you get an explosion that's like this. It basically squashes the things out because the first part hits it first, and it doesn't actually make the explosion, the thing ignite thermonuclearly. So, and this was a problem that both the Americans and the Russians had. The Americans actually tried to use the first computer to try and solve it. So you had to find a way to change this shock wave. Okay. And so what they did, it was very clever. They wanted to change the shape from this, they wanted to flatten it out, and eventually they wanted to bend it in so that the whole thing would like crush the core. And so what is true is that the speed of sound, which is effectively how the information propagates, is different depending on the density of your material. Okay, so if you shout in air, your information travels slower than if you actually take a hammer on a steel railway line. So if you wanted to hear a railway line come, that's why you have these people in the videos like leaning down and listening to the railway line rather than listening up for the whistle up in the air, is because the information along the track will travel faster. So the denser you make the material, and this is not true for all materials, but for most of them, the denser you make the material, the more effectively the energy is transferred, the faster the characteristics run. And so the faster the solution runs. So what they did is they took their, basically, let's say, whatever they exploded, TNT or whatever, and then they mixed it with stuff that made it less dense, and then over here they had a really dense core. So what then happened is you make the shock, or not less, or anyway, they made it that it slowed down. So you make the shock, they had a change of density over here, and you made it that it slowed down. I don't think this outer must have been denser then. And so it slows down over here, and this end part then had time to catch up and change its shape, and then it squashed it together.
Also, the problem was that because it's circular, could I say that like the top of the curve sort of moves faster than the other point, so they slow down the top, so it could move.
Now they slow down the center. Yeah. So here you explode here, you have a shock wave that has this shape, circular around the local thing. Then you had to slow down the central part so that the other ones could actually catch up, and then it compressed the core. Yes, they bent it all the way. And then when they bent it like this, the other detonator that happened over here would then join as well. So eventually they had a core with like a whole bunch of detonators, and each of them had a segment like this that you could shape the shock that hit the central part. So that ends my story of shocks. What you need to know is the basics of how you calculate it, how it's connected to the characteristics, how you work out that jump condition. But know that you're only scratching the surface. There are actually a lot of engineering. This type of engineering where you control the shock front, you actually get a lot in mines as well. Where you actually want, when you blast, you actually do sonar to find out how your shock is going to go, because you don't want a surprise. You use it in demolition as well. And you use it to check whether people are telling the truth about how much exploded and how much is actually currently being hidden in bombs. Because you can check these things simply by looking at the photographs.
So this, the uranium part, was this during the Manhattan Project?
This problem, yeah, was it's called it's an explosive lens or something. It's literally, yeah, that's where it started. That's where the problem became most urgent, and they put in a lot of money to try and solve. It was also the first time that they actually could use a computer, because most of these solutions were known for a while. There's a set of blast solution. There is a story that the Americans had the computer to try and solve this problem, and the Russians were very far behind technologically. And the blast solution was there. The Americans didn't even look for an analytic solution, and the blast solution they actually found an analytic solution that describes it. So they made do with what limited technology they had and came up with a brilliant piece of mathematics. So, yeah, it happened during the run for the bomb.
I feel like it was a waste of material. All the fighting, like amazing things came out of it, but we could have used Einstein and Oppenheimer to do much more crazier, more amazing stuff.
Yeah, no, I mean, waste of material, waste of life. Have you read so actually I'm going to stop the video now, because have you read what happened? There's some very beautiful stories of people that wrote that were actually in Hiroshima and in Nagasaki, that actually experienced the bomb being dropped on them. And there's a story that I loved. That's sort of a story of hope in spite of the fact that you know you're going to die. It's a story about this girl that got leukemia due to being in the bomb and describing it, and then describes how she sees her body deteriorate, how the bone marrow begins to fail, how she knows she's dying. And then yet she believes she's going to live. And the story is called 1001 Paper Cranes. And there's this belief that if you could fold 1001 paper cranes, then she would live. And, you know, and in some sense it was hopeless, and it describes her decay, her physical decay. But it also describes how, as she went from hospital to hospital, these paper cranes, like 1001 paper cranes is a lot. She carried the hope with her. And she didn't manage to finish folding them before she died. But then eventually everybody else around her still saw life. And they finished it for her, and they buried her with her 1001 paper cranes.